The next object that I want to talk about in abstract algebra is the idea of a ring. And a ring is just a set together with a few properties. So I just want to list out the properties and then we'll talk about a few examples. So a ring is going to be a set R together with two operations. We're going to think of one of the operations generally as addition and the other one is kind of generic. We'll call it star again. And it has to satisfy the following conditions. So the first is that it's going to be closed under addition and multiplication, meaning that if you were to add two elements in the ring, or if you were to multiply two elements in the ring, you get another element in the ring. And this is for all values A and B in the ring R. Okay, so that's called closure, meaning that if you were to take any two elements in the ring and combine them either with the addition or the other operation, you get something else in the ring. So that generally is called closure. Associativity is an operation, is a property that says that if you were to combine three terms, it doesn't matter whether you associate the first two first or the last two first. So for example, with addition, you could write this as A plus the quantity B plus C is the same as A plus B plus C. And with multiplication, it's going to be the same thing where the pluses and the times are interchanged there. So this is again going to hold for all values A, B, and C in our set R. Okay, so that's called associativity. And then I want to talk about some properties that addition and multiplication have separately and together. So the next property that we need is what's called additive commutativity. So commutative just means that the order doesn't matter. So if you add two elements, the order doesn't matter. So this is a property of all rings. Okay, we do not require the same thing for multiplication. So that's not a rule. We're not going to talk about that. We want an additive inverse to exist. So existence of an additive inverse. And I should specify specifically an additive inverse, which we're going to call 0. So that means that there exists some element, say 0 in R, where A plus 0 and 0 plus A are the same. So those are both A. So the existence of an additive inverse. And typically we'll write, oops, I skipped one. That's not an additive inverse, that's an additive identity. We need that too, so let me just fix that. But then we also need additive inverses. So the additive identity is that there exists basically a 0 quantity, something like 0, so that something that you can add to everything else so that it leaves the other thing unfixed. There's additive inverses, and that means that for all values in our ring, there exists another value in the ring, call it B, so that A plus B is 0. Of course, we'll write B as minus A since we're talking about inverses with respect to addition. So just like before, when we were talking about groups, when we have inverses with respect to addition, we'll use the minus A notation. A few properties that they have together in how addition and multiplication mix. There's distributive properties. So if you were to take A times B plus C, or A plus B times C, these are really separate properties because remember that we're not assuming anything about multiplication. So it's possible that A times B and B times A are not the same. So you have to kind of do this in both ways for this to work in general. But what you get is what you would probably expect if we call this a distributive property. You would get A times B plus A times C. And you would get A times C plus B times C. Notice that now that I'm worried about the order of A times B, I have to be careful that if I multiply on the left by A here, then I multiply on the left by A here as well. Okay, and likewise, if we multiply on the right by C, then we multiply on the right by C over here too. Okay, so this is for all triples A, B, and C in our ring. And then let's see what else. I think there's only one other example or one other quantity that we need, one other quality that we need, and that's the existence of a multiplicative identity. Okay, so the existence of a multiplicative identity, which kind of plays the role of 1. So there exists, I'm just going to call it 1 in our ring, so that A times 1 and 1 times A is A, and that's true for every value A in our ring R. Okay. So all of these together give us a ring. I think the best and kind of the canonical example of a ring is the set of integers mod n. I've been kind of avoiding calling this a ring up until today. But here the integers mod n, this is the same set as before. It's just the set of integers 0 through n minus 1. That's kind of the canonical choice for the equivalence classes. We're just going to use 0 to n minus 1. And here, addition and multiplication are done mod n. Okay, so this is addition mod n, which we talked about before, and multiplication mod n. Again, just to give you an idea how this works, if you were to take 7 plus 8, you would get 5. Because 7 plus 8, if we were to work in, excuse me, I forgot to mention that I'm going to work in Z10. So if you were to take 7 plus 8, you get 15, which is 5 mod 10. And if you were to take 7 times 8, you would end up with 6. So again, you have the usual things of closure, existence of inverses. So here 1 is the multiplicative identity. And so the existence of an additive inverse. So 8 has an additive inverse of 2, right? 2 plus 8 is 0 in this crazy land. So that's what the ring of integers mod n is. Again, this is, I think, the most important example of a ring. You can come up with others, such as the set of real numbers with addition and multiplication, the set of complex numbers with addition and multiplication, the set of integers with addition and multiplication, the set of rational numbers with addition and multiplication, the set of matrices with matrix addition and matrix multiplication. You could come up with the set of functions where the ring that you're studying is maybe you can add two functions together and then you can compose them, or you can add two functions together and then you can multiply the two functions. And there's all sorts of rings that you can talk about. But again, the one that's going to be the most relevant for us in the cryptography section will be this. I can now officially say what this is called. This is the ring of integers. So the ring of integers mod n. Okay, so that's going to be the one that's most important for us. And as a runner-up, the second most important one, just as a reminder, is the multiplicative group Zn with a x above it. So this is the multiplicative group, again, the set of elements in Z sub n that are relatively prime with n. Okay, so this I think is our runner-up for the most important for what we're going to do in the cryptography section. This is the multiplicative group. The multiplicative group mod n. Okay, and so those are going to be two really big examples for us.